Hey everyone, so we're moving on to the next unit, which is all about dynamics. This is basically the idea of forces. So what we're going to do is we're going to start with Newton's laws of motion and then build from there. I do want to point out that a lot of the stuff that we've talked about before will still play a factor here. We're going to be constantly reviewing and going back to previous materials, so just keep an eye out for that. Now, the first thing I want to do and what I want to focus on this is really kind of some setup stuff for forces. Basically, the main thing about forces is that it's been known for a long time about this idea of forces. You know, philosophers like Aristotle and Archimedes, they knew about this. The problem was that they didn't have the full picture of what was going on. And in particular, what they would do is when they were trying to look at scenarios, they were coming up with the wrong understanding because they were missing key information, in particular about friction. For example, if you're looking at a book that's on the table, you know that the object won't move until you physically apply a force to it. This is something that we all know, and they even knew it. But the issue that they had was they felt that the once you apply a force, the object moves, and that force is required to keep the object moving, and that if you were to remove that force, the object stops moving. But they only thought it was because of the force applied. They didn't realize that there's friction there. That by you no longer applying a force on an object, it turns out that the reason it slows down isn't because you're no longer applying a force to it. It's because friction ends up being an unopposed force that eventually slows the object down. So they were coming up with incorrect information about what was going on because they didn't know about these invisible forces like friction and some other things. It wasn't until Newton came around that really developed the concept of forces to its entirety and to its fully. He also did a lot of things where he came up with the concept of gravity. He explained it for planetary motion, and he also came up with calculus. So he actually is pretty much the pioneer of the two seemingly toughest AP courses, AP Calc and AP Physics. Now, the basic definition for a force is that a force is an action or interaction that causes a change in motion. It's any push or pull that changes the motion of an object. Now, I want to actually focus on this a little bit. What do I mean by change in the motion? Does this mean the speed? Well, speed does is included in the idea of motion, but when I use the term motion, I'm actually using it in a much more general case than speed. Because not only will force cause the speed to change, but it will also cause the velocity to change. So the force is changing, it can be increasing the speed, it could be used to decrease the speed, or it could be used to change the direction. Now, this is just another way of saying that the force will cause an acceleration. So I can also reword this to say a force is an action that causes an acceleration in an object. So if an object is accelerating, that means that there is a force being applied. It's important to note that because of the fact that forces is very clearly related to the concept of velocity and acceleration, both of which are vectors. Forces is also a vector, which means that direction matters a lot. And we also measure forces in the units of newtons in honor of Sir Isaac Newton. Quick side note if you didn't know, any unit that is a capital letter is a unit that was named after a scientist. For example, joules, unit of energy, is named after a scientist who did a lot of work in the area of energy. Kelvin, Fahrenheit, Celsius, ohm, volt from voltage, ampere, all of these watts, all of these are scientists that have done significant work in their field and have been given a unit named after them. So any unit that isn't a capital letter, like meters, grams, seconds, those are not named after scientists. Just interesting side fact. Now, we're going to talk about a bunch of forces, but it's important for me to just to kind of lay down the foundation that there are actually four, what we call four fundamental forces, meaning that if I were to try to think about like the origin of all these other forces that we're going to talk about, their origins can originate from one of these four forces. Um, so we're not really going to do anything with this. This is more of you being aware that this concept exists. So the first fundamental force is the gravitational force. This isn't a very long range force. In fact, it's actually technically considered infinitely long ranged. The idea being that the gravitational force that I feel with the Earth, because I'm so close to it, doesn't go away just because I go somewhere else. Even if I'm on the moon, I still technically feel a gravitational force on the moon caused by the Earth. It's just going to be significantly small and uh, barely even measurable because of my far distance. I can even go to the other edge of the universe, and I would still technically be exposed to the gravitational force from Earth. It's an infinitely long range force, and it's always attractive between any pieces of matter. So any two objects, us and the Earth, the moon and the Earth, a pencil and a pen, separated by some distance, all forms of matter will exert a attractive gravitational force. Now, the one thing to note though is that this gravitational force is actually extremely weak, meaning that we don't actually notice it unless we're at much larger scales, typically planetary scales or moon scales or asteroid scales, essentially what we would call celestial objects. We can find the gravitational force between two pens or two people standing on Earth, but we'll notice that the value is incomparably small. Now, there's another force that's actually very similar to the gravitational force. In a lot of ways, it's almost can be seen as like its brother, its cousin. It's also an infinitely long range force for the exact same reason as gravitational force. This one isn't caused by the attractiveness between two pieces of matter, but actually between different charges, magnetic charges or electric charges and magnetic poles. Uh, and one difference, though, is that this force could be repulsive. Um, but compared to the gravitational force, it's actually an extremely strong force. It actually doesn't require that many particles to feel an electromagnetic force. A good example of this is if you take a comb and you brush like a plastic comb and you brush your hair with it, you'll notice that your hair starts to get frizzy. uh, that's becoming frizzy because the comb is actually separating electrons from your hair, causing your hair to become electrically charged, and those charges start to exert a repulsive force between each other, causing your hair to start like getting frizzy and separating and all that stuff. So it doesn't take a whole lot of effort to start noticing an electromagnetic force. Um, so these are actually the two most common ones, the ones that we would see the most often. And when we start going into the later part of this course, where we talk about the either AP Physics 2 or if we go into Regions Physics, uh, where we're going to be talking about them again. But the other two are not really going to be mentioned too much. Uh, these two forces are much shorter range and they only occur at the nuclear level. So, unless you're doing something with particle physics, you're not really going to be exposed to these two. The first one that I want to talk about is the weak force. So this is very short range. Again, it's happening at the atomic scale, so very very small. The only thing that's useful to know is that it's what's responsible for radioactive decay. When you learned in chemistry about certain elements being unstable and decaying to lower numbered elements on the periodic table until it becomes a little bit more stable, it's because of the weak force that happens. That's pretty much it. And then the other one's called the strong force. This is actually the strongest force there is, hence the name. It's actually what's responsible for keeping the nucleus together. Again, as you remember from chemistry, the nucleus holds the protons and neutrons. In particular, though, the protons are positive charges. And as we know, like charges repel. So having these protons so close together is like taking two extremely powerful magnets and trying to push them together. They'll constantly push harder and harder the closer we get them. So how are we able to overcome this repulsive electromagnetic force? The strong force. Once we get two charges close enough, the strong force takes over and actually brings them together. And it's actually how we take advantage of trying to do any form of, um, you know, uh, fusion of elements, essentially by essentially taking the nucleuses that would naturally repel each other due to their strong electromagnetic force, getting them close enough through just slamming them at near light speed until they get close enough for the strong force to take over and fuse them together. But like I said, we're not really going to focus on that too much. Instead, we're going to talk about the variations of these fundamental forces, what I call the common forces, the ones that we would normally be referring to. Um, you shouldn't have to write a lot of this stuff down, but it is useful to know. It's something that we're going to be constantly hitting though throughout the this unit. So the first super common force is the force of gravity. Basically, it's always present. It's what's keeping us on the Earth. It's keeping the moon around the Earth, all that stuff. Very commonly, though, this is going to be referred to as our weight. So we're going to use the symbol F sub g to represent force due to gravity. You're going to see this type of notation a lot, where we have the symbol and then a sub symbol to kind of represent the type of force. But if you ever see a question that talks about weight, they're referring to the force due to gravity. The normal force, F sub n, this is a contact force. This is what we feel whenever we touch an object. So when you touch a table, when you touch a wall, when you touch the floor, we're experiencing a contact force, a normal force from that surface. So anytime you're touching an inanimate surface, you're experiencing a normal force. And the reason we call it a normal force is actually because of the fact that the direction that the normal force acts, it acts perpendicular to the surface. So the floor exerts a normal force pushing us up because that's perpendicular to it. The wall would push a horizontal force towards us because that's perpendicular to the wall. If you recall from math, when we talk about perpendicular to some surface, that term is actually called being normal to the surface. Uh, Another very common force is the tension force, F sub t. This pretty much exists like anytime we're talking about an object being pulled by some sort of rope, string, cable, there's a tension force. An applied force, this is actually important. This is when a person is physically touching an object and exerting a push or a pull onto it. It's important to note while making while being careful with these forces is definitely helpful. Obviously, you can always kind of be a little bit wishy-washy sometimes, but it's important to try your best in using the terms properly. A good example is that if I was pulling on a wagon using a rope, You would not say that the wagon is experiencing an applied force. You would say that the wagon is exposed to a tension force because the wagon is in direct contact with the rope. So the rope itself is what's pulling the wagon forward, not my applied force, but the tension force. Uh, the only thing that's exposed to my applied force is the rope, the thing that I'm physically touching. So that's important to note. This can play a part in some later cases, as you'll see later on. Though, like I said, you are able to kind of um, not have to worry too much. Frictional force, F sub F. This is a force that opposes motion. Basically, whenever we have two surfaces touching, very similar to the normal force, we're going to end up getting friction. So, in particular, if we try to rub two surfaces, uh, I guess you could say that not just with two surfaces touching, but rubbing or attempting to rub will give us a frictional force. One thing to know is that it's usually not going to be present unless they say otherwise, or as we'll see later on, if the values, if something seems like it's not going to work out uh, with it being without friction, friction will then be brought in to kind of like normalize the scenario. I'll explain that when we get to a scenario later on. Centripetal force. This is something that we'll definitely talk a lot more detail in the next unit. Uh, but I'll just say it here that the centripetal force is a force that we experience anytime we move in a circle. That one's easy to see. C stands for centripetal. C also stands for circle. Take it back to Sesame Street. Now, some not as common forces, again, these are forces that we're probably not going to be experiencing too much, or at least they'll be very, very niche type forces. The gravitational force. So, this is the force between any two mass objects, and it's only attractive. And like I said, it's usually only used for a very massive object like planets, moons, asteroids, stars, galaxies, whatever. Now, a very quick side note, some of you may have noticed that in the fundamental forces, there is a gravitational force. In the common forces, there is a force due to gravity. And then there's this one, which is gravitational force. Isn't it all the same? Yes and no. Um, Technically, gravitational force and the force due to gravity are the same because they're both forces caused by the effects of gravity, caused by the effects of the attraction between two masses. However, the terms used, gravitational force versus force due to gravity, are used in different contexts. So when we mention force due to gravity and we say that specific phrase, we're usually referring to forces caused by you being on a planet exposed to a planet's gravity. You know, you are on Earth. You talk about the force due to gravity. You're on the moon, on Jupiter, on Pluto, on the sun. You find the force due to gravity based off of the acceleration due to gravity on that planet. The gravitational force, on the other hand, is when we're trying to find the force between two objects that may or may not have gravity at those locations. You'll see what I mean when we get to the next unit, where we actually go into a little bit more of a deep dive with this. But just know that the term gravitational force and force due to gravity are used in slightly different ways, and they also hint at using slightly different equations. All right, so continuing on, the electrostatic force and the magnetic force. These are other forces that we'll talk about. Well, we might talk about later. Electrostatic force is going to come up in the region section, and if you continue on into the AP Physics 2 section, along with the magnetic force, that appears in the AP Physics 2 section. Basically, again, these are the attractive and repulsive forces between charged objects for electrostatic or magnetic objects in the magnetic force scenario. All right, so that was just a quick little rehash, or I should just, blowing through the concept of forces. Like I said, we'll be going into a lot more detail with these, so don't think that you need to have a very clear understanding of what forces exist. You're going to pick it up naturally. The last thing that I want to talk about is this idea of free body diagrams. So this actually ends up being extremely important. One of my go-to statements is that anytime you are stuck on a problem where you're dealing with more than one force, my recommendation will always be to draw an FBD, draw a free body diagram. So, because it really helps visualize all the forces acting on the object. Now, these free body diagrams, or FBDs as I call them, are very quick sketches of an object. You don't really draw anything else, you just draw an object. In particular, you simplify it to a box, make your life easy. Don't spend any time putting any sort of detail. It's a box. And what you're going to do is you're going to draw arrows on that box to represent the forces acting on it. And you're going to show the arrows going in the direction of the force, of each force and what they go in. So, a good example, because I think it works best with an example. Let's say we had this scenario where a fireman's lifting a little boy out of a well using a rope. The boy weighs 500 newtons. They want us to draw an FBD of the boy. I wasn't really clear with this scenario, but I want an FBD on the boy itself. So I start with a box. They tell us how much the boy weighs, so I know that there's a force due to gravity pulling him down. I know that this is, FG, and then because of the fact that the fireman's lifting the boy using a rope, we know that there's a tension force going upwards. So my forces will look like this: FG going down, FT going up. So this is my FBD. Now with this, I can then take it one step further. I know that the weight of the boy is 500 newtons, so I can add 500 to my FBD. And if I was given a little bit more information, I'd be able to use this to figure out what the tension force is. I'd have enough information. And that's kind of how the FBD ends up working. All right, so let's do a few practice questions. So pause the video, work itself. We'll go over in a second. All right, so here we're going to draw two FBDs of an egg falling from a tree. And in both scenarios, well, for the first scenario, we're going to neglect air friction. So we're going to start with the box. We have the force of gravity pulling down, and that's it. There's no other forces. There's no normal force because there's no surface. There's no tension because there's no rope. There's no applied. There's no person touching it at this time. So the only force is the force of gravity pulling it down. The second FBD is going to have us include air friction. So the beginning stays the same. We're still going to start with the box. We're going to have the force of gravity going down. That didn't change. Now what we have is air friction affecting it. You may have to go back to what I said about air friction, but one of the things I said is that air friction opposes motion. So this object is falling down. That means that the air friction is going to be pushing up. So I wrote it as FAR for the force of air resistance, but it's the air friction. You could have also just called it F of F. Doesn't matter. All right, here's the next question. Pause the video, work itself. We'll go over a second. All right, so for here, they want an FBD of this on the person. So once again, I start with a box. I know that there's a force of gravity pulling them down. They say that the very first rope is pulling directly to the left. Because I know that there's going to be two ropes, I want to actually call this FT1, just so that I keep track of it in my later questions, like if I were to kind of do some calculations. And then they say that the second rope is pulling up and to the right at some angle. So this is what my FBD will look like. And there's nothing else. Again, no normal force, no applied force, nothing. Now, one thing I want to actually take a break from this, and I want to make a very quick comment. So there are going to be two different types of FBDs that you're going to draw. There's going to be an FBD that you draw for me, for the instructor, for the tester, whoever is going to be grading the grader of your test. You're going to be doing it for the AP, whatever the the aspect is. You're going to be drawing an FBD for someone else at some point. When you draw the FBD for someone else, this is what you draw. Exactly what I show here, nothing more, nothing less. But when you're drawing an FBD for yourself to use as a way of simplifying the problem, to visualize a problem, whatever you want to say, one of the things that you're going to have to do is you're going to have to do something about this tension force. This tension force is currently acting at an angle. Just like in the angular projectile scenario notes and scenarios where we couldn't do anything, we had to break it up into components, we're going to have to do the same thing here. So what you are going to do is you would draw the FBD like this if you're doing it for yourself, and then take this tension force and break it up into two parts. So I'm going to call this FTY, and I'm going to call this part FTX. Because I know that this tension force is acting both to the right and up. So I'm going to have a force that's going to the right and a component that's going up. So what I'm going to do is have this be my force. Then I have to also remember that, I might be given this value and I might be given this angle. So I need to remember my equations for how to find the components. Well, the x component would just be ft2 cosine theta, and this would end up being ft2 sine theta. From here, now I have a much easier scenario that I can do, and I would get rid of this. All right, so just keep this in mind, the difference between you drawing an FBD for yourself versus drawing it for the instructor or grader. All right, here's the next question. Pause video, work itself. We'll go over in a second. So, if you recall, the normal force always ends up acting perpendicular to the surface. So on this diagram, if I draw the normal force, it would go up like this. So I'd want to find one that looks like that. Try not to get too confused with these angles. My answer ends up being choice 3. So there's one last thing that I need to talk about when it comes to FBDs and free body diagrams. As I said, when it comes to the diagram that you draw for yourself, you can stop at pretty much what we did right in the beginning, where you just draw the arrows and that's it. Maybe label them, whatever. But there's one other thing, that if you're drawing a diagram for a grader, for a test, for a teacher, one thing that you want to try to do is scale the size of your arrows to represent their magnitudes. Now, you don't need to use a ruler to accurately draw the arrows to scale, but what I mean is that if you know for a fact that one arrow is bigger than another due to the fact that the net force is going in a certain direction, you want to make sure that you exaggerate that. A good example would be something like this. I have an object that's accelerating to the left. I'd want to draw it and make sure that whatever arrow is pointing to the left is exaggerated to be much bigger. So you can immediately look at it and say, there we go. You do not want to leave it up to the grader to have to take out a ruler, because the AP has said that if it cannot be discerned with the naked eye without the use of a ruler, then it doesn't count. A lot of times what you'll see is they'll end up having questions where there'll be lines going like this, so that what you can do is you could basically just quickly look and see, like, okay, this is 3 lines across, this is 6 or 7 lines across, there we go, that one's bigger. So that can help you make sure that you're making an arrow bigger than the other. But in case you don't have something like this, I would just make sure that you exaggerate one side more than the other. And that's pretty much it. We'll end up continuing on our discussion with forces where we start talking about Newton's three laws. But for now, that's pretty much it for the basis section of this. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.